is okay. Okay.
Okay, I'm just going to start recording. So again, thank you so much for coming. We really appreciate it. First, we're going to do a quick overview of what we're going to go over today. We're going to give a quick overview of our mission profile, just so everyone is refreshed and on the objectives that we need to accomplish for this project. And then we're going to have our mechanical team talk about their progress, which then leading on to our electrical team and our embedded, and then finish up with software. So at the very beginning of our mission, we will be deployed by an aircraft, MAC, and we will be dropped from a height, and then we will then navigate our way to the hiker. We will then switch to manual mode in order to prepare and load up the hiker. And we will then navigate our way to the extraction point where MEA will then pick up the hiker, and we will then navigate our way back to HQ. So with that, I'm going to stop sharing my screen and I will pass it over to Tyler, our mechanical lead.
Hey everyone, my name's Tyler Harley, mechanical lead for this project. So today I'm just gonna kind of spin the model with you guys and kind of go through it in SolidWorks and show you what we design and go over some of the trade studies that why we came up with those design ideas and implemented them. So I will start sharing my screen, and if you have any questions or anything, feel free to interrupt me and ask those questions. It'd be really appreciated. So. All right, can you guys see my screen?
Yep.
Cool. All right, so first I want to talk about our payload retrieval, so the hiker retrieval mechanism that we came up with. So I'll show you guys the action that it's going to be doing. So this is the stretcher idea. It's going to go up and over like so. And then once it's down here, just gotta suppress this mate. It will then open and close. So to open and then close. Now, as it hasn't been modeled yet, but we are putting buckles on top of here. So as the stretcher is stored in the back, it will be stored in an open position so that when the servos close, it'll latch those buckles together and stay closed while the hiker is inside of here. And within here, we are going to be putting foam, some sort of foam in here to safely secure the hiker and hold them in there securely. And when it is closed, I know pinch points was kind of an issue. So we ended up making a gap right here. And the reason for this gap was we did some research on medical stretchers, and these medical stretchers actually went around a person and kind of scoop them up essentially like this. So this is the reason for the gap. And obviously these motions are controlled by servos and gears, just 2 degrees of freedom here. And then it'll go back to the close moment. But as the hiker is in here and it's buckled together, our disconnection method is within here, and I'll open up another SolidWorks to kind of give a good example of this. So as you saw before, the pins went through here. This is a little flap with this spring would be compressed. The torsion spring would be compressed and pushing against this latch and holding in that pin. And as we go to offload the stretcher into MEA, we would push down on this gate, it would open, and then as we were pushing down, we would back out. And then that would offload the stretcher into MEA. We thought of this idea more to try and get a more passive, so we don't have to add more circuits and servos and deal with magnets or anything like that. So this was our payload idea. And to back these ideas up, we did a trade study The trade study consisted of 3 different ideas. So we had a treadmill idea. This treadmill idea dealt with, think of the lower portion of the treadmill that you run on. This would be in the middle of the whole vehicle. And then as we came up to the hiker, it would operate and drag them onto the essentially stretcher. And then we had another bucket scoop idea. This one, if you can think of a skip loader, the way the bucket, like scooping up dirt, we thought that would work. So that's the other idea we dealt with. And then the scooper lift idea is our claw idea that I just showed you. And then these FOMs are a criteria that we decided to weigh on. And within this, we decided what was greater in value and what we thought would weigh more in scoring the designs. And within all of these, we can go back here and you can see the weight that was added into this. And it shows here that the scooper lift one here, our claw mechanism, won out. So this is the reason why we ended up going with this design. Was there any questions regarding any of this?
Yeah, I got a couple quick questions.
Yeah, go ahead.
So my name's Alex Hikert, and then I guess my first question is this assuming the hiker is going to be on a flat ground and everything's going to be flat? Because I can see that if you're trying to pick up a hiker that's at a slight angle, you could potentially have some issues with that.
Okay.
Unless you're assuming. Sorry, go ahead.
This was definitely assuming a flat ground, but there's so within here, this whole mechanism right here, these pins are going to be on a bearing so that it would keep it level with the ground. So if we were to press against the ground, we thought that it would go level with the ground.
Gotcha. Yeah, it should work. Okay.
And then also I did 3D print something. I don't know if you guys would like to see that. It's a very generic version of the triangle, but it kind of works like picking up a pen. Let me see, I just got to adjust my camera, sorry. So can you see this is the pen right here. And then these are the 2 triangle pieces, essentially what is there. And then as it closes, as I push, we can see that it picks it up pretty simply. So that was our kind of verification with that whole thing.
Okay, yeah, I like that. Okay, my next question was, where's your CG when you're picking up the person and pivoting back onto yourself? Because if CG is too far forward, it's gonna tilt you off on 2 wheels. So I see a bunch of those colored blocks. I don't know what those are, but that might be something you would want to move.
Yeah, we are getting to that. So in terms of CG, we're thinking the hiker is going to be less than a pound. So I think that was within our criteria that we changed. And due to that, this whole structure was going to be 3D printed and be pretty light. And then all of these components right here, we're going to get into, but these are the electrical components that we showed for packaging purposes and all that. But can you ask your question again? It was about the CG of holding the hiker there and then tilting on 2 wheels?
Yeah, so if you're picking up the person, say your whole CG gets moved forward, it could be pushed eventually ahead of your front 2 wheels because it looks like you have a lot of mass up front, but not as much further back. So I'm worried about your 2 wheels getting tilted off, so you're basically on your front wheels and you're stuck trying to pick up that hiker.
Okay, all right. I think looking right here, we have plenty of room to move this back for that case, to move like this whole, the gear system and all of that back. All of these components are pretty much circuit boards and all that. The LiPo battery is also in the back right here.
Okay, so that'll be pretty heavy.
Yeah, so that's another reason why we put that back there. Yeah, that's a good point. You bring that up. We'll definitely, we haven't done a full CG analysis on this yet. We're just getting together and trying to package everything from what we can see by sight. So.
I gotcha. Okay. Right. And then the last question I had was on the trade table. Was that a trade table you put together, or did you do it with a team, or is it a couple different people working on it?
So
Because
this,
I'm looking at the final values, and you had 49 for one, 45 for the other two. That's close relatively, and I understand why you did trade table. It's kind of one of the best things to do for this, but at the same time, I absolutely hate them because it's so much is opinion based. You know, what's your level of reliability? You can do some reliability factors. Granted, in our industry, it's a lot of hand waving, but a lot of it's not as solid. But like packaging, you can get dimensions and all that kind of stuff. So a lot of it's subjective, I would say. So I don't know if you did it with a team or one-on-one or just yourself, but that's always
so
something to consider.
yeah, we did it with the whole team because this was
Okay.
pretty much the major component of the vehicle. So I took the whole team of about 18 students and we kind of scored this all together and got everyone's input on that.
Okay. That sounds good to me then. Otherwise, I like the design. I think it's pretty cool. It's pretty unique, but it's simple is what I like.
Mm-hmm.
You're going to want some kind of bearing on the other side. So when it rotates,
On, sorry,
it's
which side?
hard to show. Back on the three main gears, that open and close, that kind of jaw mechanism,
Mm-hmm.
you're going to want some bearing all the way to the right
Oh, over
on
here?
that side to keep it rotating. Otherwise, you're going to have it going at an angle, or it's going to be a lot of force
Oh,
on
okay.
that gearbox.
Okay, yeah, I see that. Okay.
Otherwise, I like that. It's pretty cool. Pretty simple.
Okay. Yeah, if there's nothing else on the payload, I'd like to pass it off to my sub lead.
Tyler, I did have a quick question, if
Yeah.
you guys can hear me now. This is Elise.
Hi, Elise. Yeah, go ahead.
Cool. Okay, I've joined successfully. I had a question on if you guys have looked into the sizing for the rods that are going from the actual gears to the pincher things, if you will. Just because I know you'd mentioned you're thinking the hiker is going to be no more than a pound, and at this point, it's going to be very cantilevered, and I would consider possibly, if you think it's going to be up to a pound of a hiker, what the loads on those rods would be, the ones that are transferring from the gears to the actual pinchers, and consider the fact that you do have to operate up to 15-mile-an-hour winds. And consider what the additional loads on those rods might be. I'm sure your bearings are going to be plenty strong, but you might want to back out the acceptable inertia for those for the rods that are transferring between, which is really your cantilever beams.
Okay. Yeah, we'll definitely take
They're
that into
probably good,
consideration.
but it's a nice simple calc that that ties back to your requirements.
Awesome. Thank you. Okay. Yeah. If there's nothing else, I'd like to pass it off to my sub lead, Chad.
One second. I have one quick question. Are you for the retrieval? Are you planning? How are you planning to release it? Like where exactly?
So the release is going to, this whole triangular stretcher is going to go inside of MEA, and MEA is developing a box that comes down from their VTOL, and then within there we would set it inside and then push down and then back away.
Okay, so they're dropping down a box. You're gonna put it in. You're gonna put this inside and then release it.
Yes.
Okay.
And like I said, the release is a simple passive mechanism that would push down with the servo and then back away.
Okay, great.
Are there any other questions for Tyler here?
Not at the moment. Good job.
Okay, thank you. Yeah. So like I was saying before, I'd like to pass it off to my sub-lead Chad that will talk about more of the chassis design and the drivetrain that we ended up choosing. So, and then he can share.
So my name's Chad Merkovich. I am the sub-mechanical lead, and you guys should be looking at a SolidWorks model, correct?
Yes.
Awesome.
Yeah,
like Tyler was saying earlier, we went with a four-wheel drive differential system. And I guess I'll just kind of start on the packaging side, being you guys had some concerns about that. So like he was saying, this is our camera box, which is the Intel camera that's doing more of the obstacle avoidance. And then we have an infrared sensor with the USB hub. And then this here is our micro Z board, which is, I think, kind of like an Arduino type board. So all of those components are relatively light in comparison to our two motors and the LiPo battery. So although we have not done a CG analysis around the front axle like that, we're assuming we're going to be okay. The initial intuition says we'll be okay, but we'll definitely do the calculations on that. So that's kind of how we packaged all of that. And then so we went with a four-wheel drive differential system, differential drive system. So we have one motor operating the left side, one motor operating the right side. And then it's going to be driven by timing belts. So I'll just kind of pop into our trade study real quick to show you what we compared against and why we chose what we did. So we had a two-wheel drive differential system that we were comparing against a four-wheel drive differential system, along with single and dual Ackermann steering. The figure of merits that we were comparing against were maneuverability, turning radius, number of motors was a big one due to weight, steering complexity, software and control, suspendability. We were determining whether or not we would need suspension or not, and how easily one could be suspended or another was a category that we were looking at. We had packaging, power transmission, consistency. That kind of tied into reliability of power transmission. So gear failure, part failure, those were kind of the things that we were thinking of then, and then how easily it would be to assemble. And then all of that, like Tyler was saying earlier, we compared this with the whole team, and then we gave all of our values, came to a good conclusion on that. And so the winner was actually differential two-wheel drive. And that was due to simplicity and whatnot. The reason we didn't go with that is it sort of doesn't work in reality. If you're trying to spin the two front wheels backwards and you have no power going to the back wheels, you have to overcome the static friction and the weight of those wheels to skid across the ground. And we didn't believe we would have enough power on a high grip surface if we were not on a loose gravel or something like that. So that's why we went with differential four-wheel drive over the single and dual Ackermann, which were much more complex, had a lot more points of failure, things of that nature. So going back to the model to kind of explain how all that works is, so we have two timing belt pulleys that are coming off the main motor shaft. These are 3D printer timing belt pulleys, so pretty readily available. And then we were just going to weld them together so that we can have both pulleys in time with each other. And then one belt would go in the front wheel, one belt would go in the back wheel. And then this here is just a rudimentary tensioner system with a torsion spring. That was kind of the first pass of that we looked at. More analysis would be needed to determine exact spring weights and things like that. So once we get to the pulley, the power would be transmitted into this shaft, in which we have a pin that would be drilled through the shaft, and then this hex would slide over that pin with the slot, and that would lock the power there. And then on the receiving end of the wheel, you would have that same hex that would match up against the wheel, and then nut it on the other side. So that's how the power would make it from from the motor into all the wheels. And then the way we would steer is overdrive, underdrive, one side. So more power left side, right side would allow things to turn. Those are all the main points I got. It fits within our 8x10x12 requirement given from MAC. And so, yeah, if you guys have any questions, feel free to ask.
I like your tensioner. That's pretty neat, pretty simple.
Yeah, it's pretty
It's actually
simple.
a
And
good
then
idea.
another thing I didn't quite mention is the impact is obviously a very big part of the mission. And we were kind of worried about slipping off during impact. So the way it's orientated right now, the inertia of the tensioner would continue to tension the belt during the impact. So shouldn't allow us to have a belt slippage during.
Yeah, I like it. Everything looks simple.
Can you explain the reasoning why you went with 2 motors in this pulley system over like the 4-motor direct drive?
It was mostly weight and packaging. Those were the big concerns. With these motors, I mean, they're incredibly long. Granted, we would need more power to put 2 motors versus 4, but packaging was really the big one.
Okay, so those are they DC or BLDC or?
They're DC. They're brushed DC motors that are encoded with a planetary gearbox on them. And yeah, so everything in there is all sized to spec.
Okay. Thank you.
If there are no other questions, I believe we can move on.
So is Mechanical done presenting?
Yeah, if there's no other questions or any concerns or anything like that, then that was the design that we have come up with for the whole, not the whole project, but for our initial design and everything.
I think you guys did do a really good job of weighing what your constraints were, and trying to incorporate the responses that you got from SRR. And yeah, everyone had really good feedback on, clarifying questions or, oh, this is why we chose this over something else, right? Whether it was packaging and weight or whether it was simplicity. I think you guys did a really good job. And I think that, take the comments that you had from this meeting and make sure to highlight some of those things that we had asked as clarifying questions in the, what's the next one? PDR? I don't even remember.
Yeah.
I think going in and having those, I mean, that's why we do these technical reviews, right? Is so that you can hear the questions that are coming out from us, such that you can, maybe adjust the way that you said some of the things right from the start, such that we understand exactly where all of your assumptions and constraints and why we're looking at the design we're looking at. I think it is a great decision on all your parts, really. But take those comments and try to bring them into your initial presentation when you're at the PDR with all the reviewers.
Yeah,
we appreciate feedback.
Yeah, thank you.
We will now pass it on to Steve, which is our electrical lead.
Hey, Celeste, before we just really quickly before we move on, since Elise had brought up PDR, I was kind of going to ask on the behalf of the mechanical team to the reviewers, given said I'm not a mechanical person, I don't know all of the details. Is there anything specifically that maybe you didn't see today that you would expect to see at a PDR, or just any general guidance for making sure that, all the boxes are ticked for a PDR from a mechanical standpoint?
Actually, there's one thing I didn't see. I didn't really see the whole landing, or I didn't get explained the whole landing part, or the like how you guys are planning to do the landing.
Oh, sorry. Yeah, the whole landing thing. We're going with a parachute. We are still doing calculations on it. We're very close to getting the calculations done. We're running a MATLAB code with everything to kind of get the forces on that, and then within that also goes within like chassis material selection. So we're waiting on forces for that to finalize our chassis material. The two main materials we're thinking of is aluminum and carbon fiber, and the carbon fiber is also dependent on being able to work on campus and utilize the tools there to properly like put it in an oven and properly seal them and all that stuff to make the carbon fiber.
Okay. Because I feel like you guys will probably have some mechanism to release a parachute, or I don't know. I guess that'll be a little later, but I guess for PDR, I definitely want to see the interaction between you guys and the airplane. I don't know what's called this year, and sort of the landing, because I didn't see that here yet.
Okay, yeah. Sorry, to touch on that too. We have had communication with UAV, and they developed a system to hold us in. We haven't designed it yet completely because we were just finishing up our chassis design, and this is kind of like what we're going to go with. So now our next step going forward is designing the hookups for that, and there'll be two side hookups that would essentially lock into their cargo bay area that they have for us, and then they would release those with the servo and we'd fall out of there, and then the parachute would be attached to the back side of the UGV, and then strings would be attached to the corners, and we're still in the process of figuring out which points we need to attach to the UGV to make it orientated the right way when it falls.
Okay, and for the landing, are you guys planning on, like I know last year we had the whole like foam box thing that was encompassing us. Are you guys thinking of any other supplemental stuff, or just are you going with just the landing?
So that
wheels.
Yeah, that's still in the process of we need to figure out the forces when we hit the ground with the parachute calculations, and then we'll move forward. That's also moving forward, but yeah.
Okay, just want to make sure that's getting looked at. But
yeah,
cool, looks good.
I think as far as preparing yourselves for PDR, Celeste had a really great chart from the SRR slides, slide 61, that was your path to PDR. So I think going through kind of that as a checklist, if you will, which you've done predominantly, going through the down select, showing us your CAD models, keeping in mind what, your size, your weight, your power budgets and things like that. But the other things you had listed for path to PDR were structural analysis, cost analysis, manufacturing plan, risk mitigation plan, and electric component selection. So you guys had them all in there, right? And I think just keeping that as a mental checklist for yourself, since that was provided as your path to PDR at the SRR presentation, that would be a good place to start. And like, who was it? Adon had said, your three main mechanical selections were the landing mechanism, the drive train, and then the retrieval mechanism. So just make sure that you hit that whole checklist of path to PDR for those three selections.
From suggestions for PDR, it honestly depends who you're presenting to. So I don't know if you're able to get a head count beforehand. So say you have Nicole there, she's going to be more of an analyst, so she wants to see the impacts from landing, the stresses and the motors and the gears. And if you're doing more electrical, you'd orient it more around which motors you're doing, have some of the little diagrams for wiring, what's connecting to what. For mechanical, if you're presenting to a bunch of mechanical people, maybe go with a lot simpler of a approach, but having a better overview of everything. kind of just depends who you're presenting to. That probably wasn't the most useful. But as far as what I would want to see more of is basically diving into every little thing a little bit and trying to find a clear way to present that. So I don't care necessarily how many gears you're using, really even like what kind of motors you're doing, but I want to know how everything's turning, how everything's interacting, if that makes any sense.
Animations are really good for that too, if you can get that
Yeah,
going.
and in the future, don't do any SolidWorks modifications or changes or movements in a PDR. Try and figure out a way to get a video of that beforehand, because a lot of times when you're doing demonstrations on CAD over Skype or Zoom calls, it usually doesn't work out, but so far it looks pretty good.
And GIFs are kind of subjective. Some people like them, some people hate them. I guess if you were to throw in a GIF of something simple just to get a real quick point across, that would work, but don't make it distracting.
Thank you guys all for those inputs. I wrote them down, and we will definitely take that into consideration for PDR. Steve, are you ready to present?
Yeah.
Awesome.
Let me share my screen. And everyone can hear me, see me, and see my screen. Yeah.
Correct.
Yep.
So to begin, so hi, I'm Steve Pollan. I'm the electrical lead for UGV. And I'll be touching on primarily motors, batteries, and kind of a breakdown of the way the power, our power budget and kind of our weight budget for all the electrical components. So first up, this is the motor that they were talking about. We're planning to go with a brush motor over a BLDC, primarily due to kind of our current circumstance where we're all working virtual. We deemed that going towards the BLDC would be kind of more complex virtually, as we would need to get a gearbox to get to the right torque, and we need to figure out how to encode that motor too, which again would just add more issues to manufacturing that's already pretty stressed already. So we deem going brushed, even though they're heavy, would be a lot simpler in this current environment and how we're working. So these are the motors we're going with. In terms of motor calcs, this is our torque versus RPM graph that we're pulling values from this motor spec sheet. And so this 958 up here is its stall torque, and then down here is 118, which is its no load speed. From there, this intersection point here, this orange line, this 120 ounce-inches is the amount of torque that's required to go up the hill, as we're required to go up a hill at least 1 mile per hour. And so based off having a 3.25 inch wheel or 3 1/4 inch wheel, and having this intersection point here, we get about 103 RPM, which translates to about 2 miles per hour. So these motors check out and work for our certain set of requirements. I'll be using this value later to kind of help calculate our battery size. Other than that, we've also had this torque versus current graph to kind of figure out how much current our motors are pulling. So to determine that, we created this calculator on the side where we take in essentially the wattage that's going into the motors. We take the no load RPM, convert it to its angular speed, and then get its mechanical power by taking a certain efficiency that's getting lost as it's translating through the gears and through that. And based off the load spec from the motor, we can figure out what kind of efficiency we're running at. So we found it to be about 50%. And then from there, we can vary our amperage to get different torque values. And then from there, we can all plot it all out and see where we're at in terms of torque. So at 124 ounce-inches, that runs at about here, which is about 2 amps. So in this case, we're going to overestimate and run it at 2 amps. So this is kind of all of our motor analysis we've done. So again, to repeat, we'll be using this 2 miles per hour, and we're going to be assuming that we're climbing, like worst case scenarios, if we're constantly climbing a hill at 2 miles per hour, and we're pulling about 2 amps to achieve that. And then from there, to achieve battery analysis, we essentially find the wattage per foot, and then to get to the distance, we take the wattage of the battery and divide it by wattage per foot, and then we can get out feet to see how far we're going. From there, what we do is we take and vary the battery capacity on this to figure out how far we're going in terms of distance. And so the requirement states we have to go at least a minimum of 1,500 feet. So that gets met at this value here. From there, to add on additional, this is only considering the motor. So the motor takes about 0.6 amp hours to go 1,500 feet. And then to add on to like the rest of the system, we take the idle current, which is just assuming that everything's running for 20 minutes, and we figure out that capacity. So we get about 1.67, and we add that addition to here. And so we end up having about 2.267 for that. To go 1,500 feet with idle current and the motor drawing 2 amps. And so we can produce this graph on the side here, which again shows down here on this x-axis is the idle amount of amp hours. And then from there, this is, as we vary our amp hours, we can see how far our distance is. So this red line represents our minimum, which is the 1,500 feet. And then we add an additional 20% just for a cushion and just for just extra breathing room for us. So just in case if we're running in the plane while we're getting carried in UAV, you know, we will still be on. So this is just accounting for that. And so we're planning to select a LiPo battery in this range. And so the reason why we're going LiPo is because it's a high energy density and that we deem that more important than everything else. So that's why we're going with LiPo, and we're going to pick around, I believe, 2,400 milliamp hours at 3S. And the final thing is the breakdown for power and weight. So we're looking for power, about the motor taking about 60% of what the battery is holding, then 30% for about the processing, and then finally the small last amount is about 6% for the sensors. And the breakdown for that is motors is just the motors running. Processing is the micro Z board plus the USB hub, which is running both the Intel NeuralSense and Intel DepthSense camera. And then finally for sensors is everything else, which is our IR, our gyro, our GPS, and our XB, which is our transmission device. And then for weight breakdown, it's all electrical components getting summed up and added. So we're looking at about 3.5 pounds for electrical components, with of course the heaviest thing being our motor, which is about 50%. And then from there, same breakdown as for processor and sensors and batteries. It's now added down here, with it all taking about a third of the remaining weight. We also have a block diagram that me and Jonathan both developed together. You'll see that in a bit. And then the plan moving forward is we want to develop a power board to hold our regulators, and then help with like a modular design so we can easily pop stuff in and out, and looking to wiring harnesses, wires, and developing a wiring schematic for the entire thing so we can see how everything plugs in. So yeah, do you guys have any questions for me?
Yeah, I got a few. So one thing, do you guys have a water resistance requirement?
I believe so.
So one thing to take with that is that brushed motors are most likely going to require some sort of insulation from water damage, while brushless motors are actually inherently waterproof. So you're going to have to find a way to, I guess, protect your brushed motors from the elements while still preventing it, or while still cooling it, getting your motor cooled and not allowing it to overheat. So you have to find a middle ground between that. So that's one thing with using brushed motors. But in terms of your reasonings for actually using it, I like that. Kind of one whole package, reduced footprint. You don't need another gearbox, but it probably wouldn't hurt to look into a brushless motor setup. Another thing, in terms of your calc, so I saw you, if you want to pull that up, where you use calc on an incline, and you calculated that you can hold up to 2 miles an hour. Take that with a grain of salt, because you did your calculations based on a motor that's not loaded. And I don't know if you took into account friction, your mechanical friction. So just keep in mind that, yeah, of course, this is all calculation based, so you may underperform of that 2 miles per hour. How much you're going to underperform, you're going to have to find that out. So keep that in mind.
So do you think it's better to like overestimate then? So should I look for like maybe a new set of motors that gets us like a higher value then? Or do you think like...
So I would say find a way to find out those frictional values, because right now you are overcompensating, but it's just finding how much more you need how much more motor torque you're going to need, taking that friction and specs into account. So technically right now you do have a motor that overperforms, but this is at like optimal, at your optimal setting.
I was going to actually ask a clarifying question on that same regard. I know that the 1 mile an hour while going up the 40% grade and fully loaded was previously a 1.5, I believe. I know it was one of those red values that everybody was drawing attention to during SRR. I'm sorry for being so nitpicky on that. But it does bring up a good point. Has that been changed to 1 mile an hour? And if so, it might be a good idea at the beginning of your PDR presentation to show the is and was requirements for anything that you may have asked for, I guess, relief on. Just so that we know, like, okay, this is where we're starting off with the PDR presentation.
I believe so. It was changed. I'm fairly certain.
Okay. No, and that's totally fine. I'm sure if Nicole said that was an acceptable amount of relief, that's good, and especially since it's directly related to some of your selections. I would make sure to specify, okay, this is what the requirement was. We asked for this approval. This is now, this was what the requirement was. We asked for this relief, and now this is what it is. It might be good to state those right at the very beginning so that people like me who have the SRR slides up right now, I'm like, wait a second, it's 1.5. Just so that we know right off the bat, okay, here's where the discrepancies might lie from previous information so that we know for sure, okay, a 2 mile an hour speed is, 100% more than the requirement rather than just like a different amount.
I guess, is there any other questions?
Oh yeah, I got a quick question. So you're saying that you're going to be withdrawing 2 amps per motor.
Yeah.
So you'd be 4 amps total, and then you'd have to be powering various mechanisms, your sensors as well. Do you know which battery you're going to be using? Because one thing you're going to consider is the discharge rate. Because if you're pulling 4 amps from a battery, typically they have safety mechanisms that will just shut it off.
Yeah. We're looking at this for it has a very high C rating, so it's about the max discharge rate's really high. So we're assuming that we're way under that, and we should be most likely fine.
Okay, perfect.
If that's all questions,
I got a quick question for you, Steve. Yeah. So in terms of, you guys did a really good job of going through, these are our calcs, these are how we're making our decisions. I think all of that is obviously incredibly important. Are you guys going to have, a rough schematic? I mean, I know you mentioned earlier a block diagram, but I mean like an actual electrical, schematic, even if you say, no, this is pending changes, ready for PDR, that'll show, this is the expected currents and voltages of all these different components. This is how it's all going to be hooked up. These are our drivers. These are our regulators, that kind of thing.
Not like a detailed wiring schematic where showing each wire goes. It's more like just here's the encoder. This takes 5 volts at 200 milliamps or whatever. And then this is going back to the microprocessor. That's kind of what we have. You'll see it with Jonathan. Okay. If we do need to, we can probably get out a schematic by PDR. Yeah, but that's currently in the works right now. So yeah.
Okay, yeah, because I mean, if we know the components we're going to use, we know the values that they're going to need for the most part. Even if something maybe the onboard computer will change. That's a potential thing that could be swapped, for example. It would still be good, I think, to have a functioning actual wiring schematic as sooner rather than later.
Yeah, I agree.
That would also account for all of those. If anybody here has taken Professor Tarek, you would know the kind I'm thinking of, where it shows all of the voltages in and out for each component, shows that everything is copacetic with everything else, and we didn't accidentally pick a motor driver that can't function with our battery or with our mode or something like that.
It might be a good idea to also specify your, I guess, your max linear combined load case, if you will. So, you know, here's our schematic running at its, you know, worst case sizing condition. We're going uphill at 40 degrees, going 2 miles an hour with a 1 pound guy inside the clip, and it's 15-mile-an-hour winds with whatever moisture you guys need to contain or you know, be able to take. It might be good to like define in one image, like this is the worst case load condition if all of our requirements were happening at the same time, if you will. What kind of stress would that put on your system?
Definitely, I think that's probably a really good idea to add. I'll definitely look into that.
Oh, another really silly thing, since the requirement's in pounds, it might be a good idea to have your weight estimation in pounds. I know you're well below that, but if the audience doesn't know grams to pounds, they might be like, I don't know, let me pull out my phone, check it real quick.
Yeah, moving forward.
Like I definitely did on Google.
We'll make all the units the same. All right. And if that was the last question for Steve, we will move on with Jonathan for embedded.
Thank you guys so much.
Thanks, Steve.
Can everyone hear me and see the screen?
Yep.
Okay. Hi, my name is Jonathan Suarez. I'm the embedded lead for the ERU or the UGV this year. And I'll be going over all the sensor selections in order for us to achieve the requirements. On the screen, you can see a basic block design that Steve mentioned earlier, containing all of the sensors we currently have and plan on implementing. On the screen, you can also see that they are colored. The colors represent the communication protocols that each of these sensors or motors will use. The first thing to start off with is the XBee. This will be our main way of communicating with GCS. So that will be sending GCS all of the checkpoint data that they ask for. The next thing is the GPS. The GPS will be in charge of routing the vehicle to the location of the hiker. The gyroscope, accelerometer, and magnometer, or IMU, as we've been calling it, is in charge of a few categories. One, to check to see if the vehicle can reach the degree specification, and the other is upon landing. So the IMU will receive a signal stating that it has landed. We're also including a IR sensor, or infrared sensor, as backup for our autonomous movement. It'll aid in case of a failure on the Intel RealSense camera, which is our main source of object avoidance paired with the neural stick. We've also included the motor drivers that will power the two brush motors on the vehicle, as well as the servos for the payload retrieval. Going back, and then this is all tied to our processing unit. Currently, we're down selecting from 2 units, and we've been testing each one of these. The 2 sensors that we've been testing as of right now is the IMU and the Intel Neural Stick. So moving into the IMU to start off, we've been able to successfully pull information from the IMU unit onto both boards that we are looking into using, one being the Raspberry Pi. So we were able to successfully receive information from that one. And then the other option would be an FPGA board, which we have also been able to successfully set up and recode from. So let me scroll down to that one real quick. This is all just the Linux side of it to read from the I2C device. on Linux. So right here, this is the code that we use in order for us to look at the data that is outputted. We also made sure that each of the sensors is compatible with both of the microprocessing units in order to ensure that if we decide on one board that all of the sensors are compatible with the other one that we decide to go with. The next thing that we've been focusing on is the neural stick, since the neural stick is going to be used to offload our processor with the autonomous movement calculations. We've successfully been able to run a test on this sensor for the FPGA. We did a video for it currently. This is off of a pre-built model for from the GitHub website, along with a video that we pulled from online. The reason why we're doing this is for us to test the quality and the accuracy of the neural stick in computation. The next step for us would be to run a live test paired with the Intel RealSense camera. So let me go ahead and start this video. So as you can see, we're currently, oh, well, it's buffering, but as you can see, we're currently running a real-time face detection model. And in a second, a video file should open and we should see the Intel neural stick do a computation for face detection in this case. Obviously, for the real mission, we'll need to change the model that we use. But as you can see that it uses a video and it's checking the confidence level of the object we're looking for, in this case, a person. And it'll continue to do this throughout the video. I'm just gonna go ahead and skip to the very end because the data that we're looking for appears right there. But currently at the very bottom, you can see the total elapsed time. It might be kind of difficult to see, but it reads at 70.34. And the approximated frame rates being 3.13. Like I said, we were doing this in order to test a limit test of both. We're currently in the works of doing this on the Raspberry Pi as well to determine which one of these devices will be better suited for the mission, and then make the selection from there for the processing unit. And then this is just another example using, I believe, video or photos instead. So this is a different model doing the same process. So this is with a still frame image. And then we run a computation check to check, or we run a model to check whether or not there is a person in the vicinity. And you can see the neural stick has mapped the objects it believes to be a person. Is there any questions?
Yes. Can you explain to me exactly what the neural stick is going to be used for again? I didn't really catch it.
So in order for us to save the microprocessing unit's main processor, we want to offload the work of object avoidance onto a different device, which is what the neural stick will be used for. So it's basically going to act like a computational tool and then send that data to, once computation is completed, it'll send that data through to the main processing unit.
Are you planning on having any other sensors for optical avoidance, or are you just planning to rely on the neural stick?
We do have the backup of the IR sensor, which is a depth sensor. We've also looked into a couple of different options, including LiDAR. Although one of the few issues with LiDAR is the amount of power draw that it has on the vehicle, as the power draw is nearly double that of this 2 units. So currently, for this design, we are only looking at including the IR sensor as a backup.
Okay, because I saw the neural stick working at 3 FPS. So, I mean, I think it's going to have trouble while you're moving to detect obstacles, from what I saw in that video.
Yes, this was off the FPGA. I believe from what I've seen online, obviously, I haven't had the opportunity to test on the Raspberry Pi, but we can get anywhere from 7 to 6 frames off of the Pi.
Okay. My suggestion would be maybe to look into the viability of maybe ultrasonic and other sensors if you find that these vision stuff is not working exactly, because I have a feeling that at 3 to 6 FPS and you're moving, it's going to have trouble. At least that's what I'm thinking right now.
Okay. Well, definitely look into more sensors.
Jonathan, you said that was the neural stick running on the MicroZ?
Yeah, that was the neural stick running off the MicroZ.
Okay. Yeah, I'm with the Don. The three frames per second seems concerning to me. The other question I had too. I know the camera that you guys are looking into is a depth camera, right? So it provides you 2 images. It provides you your standard image and then your depth image, right?
Yes.
So I know the neural stick is used to do, like what you were just showing it doing in terms of facial recognition and stuff like that. But does it handle anything on the depth side of things, or are you going to use that image separately in calculations for movement? What was the plan there?
I believe that we were going to use the image separately for the depth calculation.
Okay, so basically then what you're doing is you're just feeding the neural stick the actual image. It's not worrying about how far that image is away, and then you're pairing that with a depth image so that you know distances.
Yeah.
Okay. Yeah, I'm a little surprised by the 3 frames on the neural stick. I figured it would have been quicker since that's its whole shtick is, doing specifically those kind of calcs.
Yeah, we're definitely looking into trying to get a live video feed to see if there's a difference in quality. That's one of the things we're also looking into as well, because the video that we showed was like an MP4 file offline. What we want to do is see if there's a better quality based off of possibly the webcam or the Intel RealSense camera itself. So that's also the next step.
Cool. I have other questions, but I don't want to hog up our reviewers' time. So,
is there any other questions? Okay, that's pretty much it for me then.
Yeah, Jonathan, if you're cool that maybe me and you can talk, I'm super curious about the MicroZ versus the Raspberry Pi, and I want to ask some pretty detailed questions, but there's I don't want to keep 20 people tied up over that.
Yeah, of course. Yeah, I can do it right after if you'd like.
Yeah, we can do that, or maybe early next week.
Yeah, that's fine.
Can I join in on that?
Yes.
Okay.
Yeah, that'd be great, Adon. Anybody'd be welcome to. I just don't want to. There's a bunch of people here that want to look at software, and they got other things to do, so I don't want to tie them up.
Yeah.
All right. If that's all for embedded, we will wrap it up with Greg with software.
All right. Can everyone hear me and see my screen?
Yes.
All right, cool. So my name is Greg Berg. I am the software team lead for the UGV team. And before I get started, I think there was a little bit of confusion regarding the neural stick in the camera, how we're doing object avoidance and how that's all. Hopefully that gets cleared up. Obviously you can ask questions about this, but I'm going to be going over the camera we're using. So hopefully I can clear this all up for everyone regarding object avoidance. But yeah. So my team we started making a state diagram or a flow chart of exactly how we were going to plan out what our mission was. We had our mission from the beginning, and we were planning, we just took steps to plan exactly what we may need. So we have like an emergency stop, we have a confirmation we landed, we have a switch to manual control, we have the navigation, which involves the waypoint part and the object avoidance part. And that was all just to get a little, to help the team get comfortable with each other in the beginning and also plan out our mission. So here's some of our example states. We have an emergency stop just in case anything is necessary or we need to stop for an emergency, I guess. Also, we have a standby just if we need to pause the mission for any reason. And then here's an example of a different state, navigate the waypoint. It's a little bit more obviously advanced because it's a little bit more complex. So this is kind of what this looks like. Our idea is exactly how we thought we were going to do this. So we're using this as a baseline for everything we're doing now as far as coding and exactly what to do, exactly what we're going to do. This could also be seen as basically our method or function, whatever you want to call it, of exactly how we're going to code it. It's almost like pseudocode in a sense, so we can really plan out exactly what we need to do, and we plan out a lot of the logic here. Obviously, it's not perfect, but it'll do. So next, we moved on to a simulator called Weebots. And what this simulator allows us to do is to, one, practice code, and two, make sure we can implement it right. Obviously, it's not perfect. It's a simulator, so it's gonna only give us so much. But this does help us a lot as far as coding. We get a very good idea of exactly how this code works, and when we do have to end up writing this code for real, make it work in the real world, it's gonna be a lot easier. So as you can see, this robot here is chasing this white box. Its goal is to get to that. It's representative of a waypoint. And it does it updates and navigates in real time. So as you can see, when it moves, when the box moves, it readjusts and moves to it. So its whole goal is to get there, and then within a certain threshold, it'll stop at it. We also worked on, besides this, we also worked on object avoidance, and this is what this is. So we combine the waypoint navigation and the object avoidance. So again, the robot's going to be looking for this white block, and its goal is to get to it. But as you'll see, the person moving these will place some obstacles in front of the UGV, and it will actively avoid them. I'll let you watch this for a second before I continue. So it actively avoids and tries to take the slowest path, or the fastest path rather, to the waypoint. What you're seeing on the left side of the screen is what the eyes are. So we were trying to model how we did it in Weebots because it can't be perfect. We're trying to model it based off the camera we wanted, which is the Intel RealSense depth camera, and I'll go into that in a second. But we're trying to model that off of it, and we're using the way we're determining the distance to an object and to make sure we're not hitting it. We're using two cameras. It's labeled here as right and left eye, and those are actively updating with it. So as we're using stereoscopic vision, or stereoscopic disparity is what it's called. Basically how it works is you have two cameras pointing in a direction, you know the distance between them, and then you find a point on your the object you're looking at, and you make a triangle, and then you can obviously do triangle trigonometry to find the distance to that. The problem with adapting this straight to the real world is RGB cameras, or cameras that are just like any day cameras on your phone or whatever. They are not very good at discerning the difference between a flat object and an object that isn't very flat, or they have a really hard time with depth in the geometry of an object, basically. So in order to avoid that and avoid confusion, and it might not turn fast enough, or it might turn too early, or it might not turn at all. So in order to avoid that, we wanted to go with, and this is a view of the stereoscopic disparity. As you can see, the two eyeballs looking things on the bottom are cameras. You know the distance between them. You could find a point by drawing straight lines out from them, and you can make triangles and then solve for that distance. So to avoid this problem of having regular just RGB cameras struggling, we instead decided to use this RealSense depth camera. The reason we chose this is it has 4 cameras on board. Essentially 4 cameras on board. There's the RGB module, which is just a normal camera, like I said earlier. There's the left and right imager, which are the 2 cameras that are going to be looking forward. They are in infrared, so that there's an easier it's easier for the computer to discern how close and far something away is, and I'll explain more on that in a second. And then there's the IR projector. The IR projector will displays a bunch of lasers that then map your environment essentially. So this is a picture of me, and essentially what it does is it maps geometry of me. So as you can see in the foreground, the laser is much brighter, it's much closer, it's easier to discern. In the background there, it's a little bit harder, but we don't have to worry about the way, that's pretty far away. But for the immediate area, something that may look flat to a normal camera will be picked up here as something different because it realizes the IR sensor or IR projector picks that up. This then combines with these two left and right imagers to draw the points to which each one of these lasers connects. So it'll make triangles based off of all of these like laser points. So that's how we're getting closer to an estimated, more correct value. Because at the end of the day, this is all estimation based off of this calculation. It can't be perfectly accurate, but this is getting a lot closer and a lot better, and it will not confuse strange-looking objects that are not flat but not really flat, or confusing to a normal camera. And then this is what the image produces with the left and right imagers. So what this does is this is an infrared view of what this looks like, of what this picture looks like. So it's able to map the distances from the camera to these. And it does this by saying, by doing that triangle, and it color codes them. So you can look at the pixels, and based off the color, you can tell how far something away is, roughly how far something away is. So it does this in meters. So something close might be 0.1 meters, 0.3 meters. And the closer something is, it's the more blue it is. The further something away is, the more red it is. So that's how it's determining the depth, and that's how we're going to be using. That's what we're going to be using to do the obstacle avoidance. Any questions?
I had a quick question. Have you? First, I want to say I'm really impressed there wasn't any spelling errors. I know last year we had an issue with spelling errors, but have you tried this outside and see how effective it is in like a bright sunny day?
I have not, no, but I have had light coming in my my room and stuff, but no, I haven't tried it outside yet.
Okay, I would give it a try outside just to make sure that it works as effectively as it does indoors without the sun blaring. So yeah, I just want to check if you tried it outside. But other than that, it looks good.
Okay.
Do you know what the max distance it can reliably tell you? You know, like what's the maximum it can see something away from it?
It really depends on what it's looking at. I imagine it'll be affected by light. Inside, it seems pretty good. The red part on the right side of my body there, or on our right side of the body, my body there, is about 12 feet away from me right now. So it's a decent job. I don't know the specified, I guess what Intel would say the distance is, but it's definitely decent. And for our project, I'm not sure it matters that much, considering we only really care about stuff that's really close to us, as far as avoiding it, or it's a high priority rather. It's close to us.
Right.
But yeah. Anything else?
Have you, so obviously from a code perspective, and this is kind of what we dealt with last semester, right, Greg, that like, depending on the platform that you guys get deployed on, whether it's a Raspberry Pi or as MicroZ, is going to change to some extent, and time will tell how extensively, kind of what sort of functions you're going to have available to you from a Python perspective, right? So like obviously working on a Raspberry Pi, you have access to all of their, nice and easy to use kind of calls for their different IO pins and different stuff like that. But on the MicroZ, that's going to be a little bit different. So how are you guys dealing with that software-wise from your team?
Jonathan has taken it upon himself to do a lot of that. We are looking into it, we have told Jonathan that we think we should do Raspberry Pi only because it's going to be a lot easier based off what we've researched. It works a lot better with the Raspberry Pi than it does with like an FPGA. You have to edit a lot of we saw today that we have to edit like the kernel and the BIOS settings of like Ubuntu to make it work. So it's not great on FPGA, but Jonathan did say he he's handling that.
Yeah. One thing I would like to mention is that all of like the nice things that Raspberry Pi has on like whether it's a file call or even the GPIO thing, we can essentially port that over to the FPGA. All of that is interchangeable because it's all based off of the Ubuntu operating system. So anything that it's based off of, we can essentially port over to the FPGA with very minimal changes if we do intend to go that route.
Okay. And then when you showed the object avoidance earlier, which by the way, like given like I have experience with Weebots, I know what a pain that software is. You guys did a really good job. Like I'm super impressed with the simulation that you guys have. It's way more responsive than what we wrote last year.
Yeah, our team did a great job.
Yeah, you guys did a super good job. So are you handling the object avoidance outside of Weebots, like with your own, like modeling the cameras, or are you doing? Because I know Weebots has some tricks where it can sort of do object avoidance, but it's not doing. So how are you guys handling that?
The stereoscopic disparity. So we're taking,
Okay.
because it's in a perfect world and it's simulation, it's able to do it fairly easily, but it's not, obviously this isn't going to transfer to the world very well.
Okay.
Real world very well. Yeah.
Yeah, because I know last year we did some kind of tricky stuff with it being able to like quote unquote see a box, but really you're just telling Weebots like, hey,
Yeah,
that's the target.
We weren't cheating here like that. it was legitimate math. Yeah.
Cool. Very cool.
All right. If there's any other,
Actually, I had one more question. Have you guys started looking into, or how is the GCS side being handled on the software? Is GCS just going to give you, or are you guys writing something? How is the GCS side handled?
We haven't been talking too much to GCS as far. Last thing I heard was that they were going to give us a XP and make it work. As far as communication, that is.
I could touch more on that. So
yeah.
As for the visual view of XP, it's going to be it's going to be on the vehicle, but off the microprocessor. It's just going to be a FPV camera, which is a first-person view camera with its own separate receiver and transmitter. As for what data we send, we have had a meeting with them where they are expecting specific pings, essentially, or flags that they are looking for that will tell them we have cleared a certain stage. So for example, when we get dropped and our sensors indicate that we have successfully landed, they can check, we will send an additional flag, and then they'll have the FPV camera as a manual check as well. So to answer your question, it's going to be the data that we send will be data, and then they're looking for flags for mission completion or checkpoints.
Okay, because during my first year, we had the whole GCS protocol, and it was sort of completely handled on the GCS side, and then they kind of just gave us the functions just to like they just gave us their protocol and we just implemented it. So I just wanted to make sure that you guys kind of have that understood before PDR, like just the general direction of what method you're going with.
Yeah.
If I can comment on that a little bit too, just because I was involved in a lot of those early comms meetings with GCS, and I've talked to Patrick quite a bit about it. The basic idea was, instead of having each individual team write its own code and do all of that stuff, it was more what you're talking about, Adon, where it was like GCS will define the protocol, they'll handle the communication side. The vehicles are just going to have to know what to check and when to get their different signals from GCS. So a lot of that development is being handled by GCS.
Okay, and then the final implementation will be vehicle specific.
Yeah, exactly. So
but
then
the
it'll
protocol
be
is okay.
Yeah, so then they'll be able to just tell the vehicles, like, you know, here's where your different, your different stuff is stored. This is how you grab it, but they're going to handle the actual communication side of the coding. So that way we just have a consistent method deployed across all the vehicles.
Okay. And what language is the UGV going to be written in? Is it Python?
Python.
Python. Okay.
Cool. If there's not any other more questions for software, this is wrapping up our presentation. So if you guys have any questions for any of our leads, or if leads have any of our questions for NGCP people about just making sure. Cool. I just want to thank all of you guys for coming. We really appreciate the feedback that we got today, and we're excited to move forward for PDR. And yeah, thank you guys so much for coming, and I hope you guys have a happy holidays too.
Thank you. Good job, everyone.
Yeah, thank you guys.
Yeah, great
Thank
job.
you for having us.
Good job.
Thank you.
If I can ask the leads to stay back, but yeah.
All right. Have a good day.
Thank you.
Yeah, you too.
Jonathan, Greg, Adon, do you guys want to? Donna might have already left. Do you guys want to talk for a few minutes after this?
Sure.
All right. I just like I said, I don't want to hold everybody up, and I was wanting to get into kind of the weeds there. So. But
Also looks really good. Oh my goodness.
Huh?
The UGV looks so good.
Yeah, you guys are doing a great job. I'm super impressed with what I've seen, especially just the level of, given the difficult situation we're working under and the level of development you guys have all gotten. It feels like, I mean, I'm super impressed, honestly. All of you guys have done a great job. I'll dip out so you guys can have your little lead wrap up. I don't want to be in the way of that. And then Jonathan, Greg, when you guys are done, just hit me up on Discord. I'll hang out here at my computer.
Okay. Sounds good.
I just kind of wanted to say good job, guys.
Thank you.
You guys did a really good job presenting. The shortest time you guys did was like 10 minutes. So you guys really expanded on what you talked about. And I think what you guys did cover was very informational, and you guys hit most of the key points, which was really awesome. And yeah, like I said, I'm actually very excited for PDR for you guys to show off what you guys done, because you guys have accomplished a lot this semester, and just we're almost there. We're just wrapping it up. So that's cool. Nathan, do you have anything to say?
Thank you, Celeste.
Thank you.
Thank you, Celeste.
You. I'll say not impressed. Still need to work. No, good job, guys. I think we got a lot of good feedback.
Yeah, we did.
You know, even though this is, even though we got a lot of, you know, good things going on, we still got a lot of work to do before presenting a PDR. I think a huge one that I'm kind of stressing out on right now is probably doing the stress, all those stress analysis, because I'm sure Nicole is going to bite us on that. So, Tyler, Chad, and I know Robert's not here, but, you know, you guys, you know, they do a lot of the heavy lifting on mechanical side. So, you know, huge appreciation on that. And, you know, hopefully you guys can continue on the good work, and we can deliver something good at PDR.
Yeah, most of the stress analysis is coming once we figure out the parachute like the landing, the forces, because that's the main stresses that's going to happen. And we could calculate the like lifting over and all that stuff. I forgot about the 15-mile-an-hour winds on those gear shafts. So that was a good point she brought up.
And also that that like cantilever beam example that you brought up too as well. Mm-hmm. Or is that what you were referring to?
Yeah, that was what I was referring to.
Okay. So that's me and you probably have to work on cost analysis. I was thinking maybe, you know, since now we kind of have a general ideas of what parts, we can just, you know, even though we haven't purchased those parts, we could just start filling in those that Excel sheet. So then we can kind of give a breakdown of what's going to be, or what the money's going to be used for. So we'll continue to work on that. And yeah, we'll probably be reaching out to you guys.
Cool. Do we know when slides are due?
No, not at the
Do we
moment.
have a
Okay.
PDR date? No.
We just know mid-January. That's all we have.
That's when PDR is, though, right?
Yes.
That's not when slides are due.
No, that's when PDR is.
Okay.
But then take that to like a grain of salt. Typically, like I think they were kind of lenient in SRR, but I think they would want to have, you know, the presentation due a week before PDR. Yeah, I'm not entirely sure what's happening with finding out a date. But you know, as soon as Celeste and I both find it, you know, we'll let everyone know right away.
Yeah. Plus, we currently do have a slide template for PDR on our OneDrive. So make sure to be looking at that. / if you guys already have, like for the power budget, if you guys want to fill that in right now, so you guys don't have to worry about it later, and that way you can just do slight alterations of when the slides are due. That would be great. Yeah, definitely look into that during winter break. And yeah.
Let me get Greg, Jonathan, and Steve opinions on this. Did you think, you know, I know that we only invited purely like the mechanical mentors, but you know, with the list given, it just looked that way, and you know, it was unfortunate that one of the embedded mentors couldn't make it. But you know, would you say you would want, you know, more, I guess, options for mentors so that, you know, you could get even more feedbacks? Or would you think just by having a Don and I guess, you know, Jeff as an internal reviewer, you think those would be enough, or would you want to have more options?
I want more options. I think
More options?
Yeah, I think a couple more people would be nice to have. That, because like mostly what I'm looking for in this is what Northrop would say about, you know, what is Northrop looking for specifically from us in terms of our field? Because that's what I, you know, for like PDR, whatever the case may be.
Yeah, same. I mean, I just bug Jackie basically on a daily, so.
And Steve, I won, by the way. Less sums.
Fuck. All right, whatever.
I'm for right now, I'm okay with not having a ton. It's just later if we have more reviews, I would want more, just because I'm going to get more into coding and making sure I'm more concerned then than I am now, I guess.
Yeah. Okay.
Yeah. So right now it's not a huge deal, but like a Don and Jeff is plenty probably. But yeah.
Okay. And Celeste and I would we're gonna talk to Jeff to see maybe if Nicole could bring in some more mentors specifically for you guys.
Yeah.
Okay, cool.
Sounds good.
And with that, once we get it, feel free to reach out to them and even like set up maybe like a bi-weekly meeting with them. That would be really cool. I know SIF Systems does that with their mentor, MGCP. So yeah.
Okay. They're in embedded right now, Greg.
Yeah, I know, I saw them.
Okay.
Yeah. Are we good here?
Yeah, I think we're good here. All right.
All right, cool. I'll see you guys.
Nathan,
When do I see you guys
stay
next?
behind.
See you guys.
Tuesday, I guess. Yeah.
Thank you.
All right, later, guys.
Bye.
Nathan, how do I deal with the recording?